Okay, next one. Christina, help me out here with this, please.
Network interface card. Provides a physical connection between the computer's expansion bus and the network cable. Boost the digital signal from the computer. Change the data stream from wide stream to narrow stream parallel to serial conversion. Move data to and from random access memory and manage the flow of data to and from the network cable. Buffer the data from the computer.
Okay. So prior to this, there's also the modems that do the same job. Obviously, that technology is very antiquated, still being used in some countries, including instead of SneakerNet, they're using pigeons. No, I'm not lying. They're using pigeons. They basically strap a USB to the back of that pigeon's leg, and the homing pigeon knows where it needs to go fly. And since now I can send gigs compared to 9600 baud rate, that's obviously much faster. So his job is that it's going to change all zeros and ones, and he's going to slap, we're going to find this a little bit later, but he slaps a little label with extra information about what you are. So the application has its own ones and zeros. Everything in there has its own ones and zeros. When he gets to this point, he basically says, hey, this is the MAC address of this pack. Here you go. He's the one that's able to obviously decipher back, is this my conversation? Should I be receiving this? Yes. So here you go. Back to you. Any questions on his job? So he connects directly to a network cable here. The network cable usually gets connected to a switch or a Soho routers, depending on but the job at that point is a switch, usually directly to a switch. Any questions? Doubts on a network interface card? So when you see NIC card, that's what it means. Network interface card. Any questions? MAC address. This is beautiful. Here's the number right here as an example. The media access control itself is built into the actual NIC card. It's actually inside, you could say, a ROM chip in there. It contains 48 bits that are expressed in 12 hexadecimal characters. This is obviously to facilitate the process on the network. All hardware addresses have an area in the front, which are these three here, represents the actual manufacturer. If you look up the first three there, octets, of who is that MAC address, it'll tell you who created the actual card. The latter is the serial number associated to the card. This is what the switch uses to be able to identify who you are. The MAC address is basically utilized in this way. Christina wants to talk to Jordan. Christina screams out, I want to talk to Jordan. Jordan is a PC, just play along here. What happens is when you first turn on your computer, both Christina and Jordan say hello to the world, usually to try to find out some type of information. When they do that, this switch now stores your computer name to a table associated to this MAC address. Now he knows exactly what port Christina is connected, physically connected to this switch. We can pretend that this switch has 48 ports. So as soon as I already know where she is, and I know where Jordan is, I'm able to now, with ease, be able to basically route the packages without talking to anybody else. Pretend now that Carlos got on the network and somebody wants to talk to Carlos, but he turned on his computer, but basically we'll pretend he never even got an IP, just for lack of a better exercise. Obviously, if he talks to the proxy server or anybody, is going to give him that. So if I don't know who he is, what's going to happen is the switch, I'm going to scream out, Carlos, are you here? Or who is Carlos, better yet. Believe it or not, if you look at the packet, it actually says who is, and it says the computer name. soon as that packet goes out, if Carlos is on the network, will respond to me saying, I am Carlos, and here's my MAC address. As soon as I find that out, at that point, now I update my tables, and with ease, I can now route within the LAN via MAC addresses. I'm not talking in IP, only MAC addresses, the packets. Anybody have any questions on what MAC address is and how it is important in reference to where it is and how it speaks in the network and what it's for? On the right here, I would like you guys to go into your actual activities of classwork. We're going to be playing Flippy Bit. And if anybody can beat me, which my top score is 50, I will gladly circumvent when I finish explaining now the exercise. I'm sorry, go ahead. Somebody had a question?
Yeah, how do you turn off the music? Because it's really loud for me.
That's a good question. I think I usually just turn off the music itself, as in the sound, when I start playing that. So you could turn off the music when we get to that point. So what we need to understand is hexadecimal. Hexadecimal is a 15 base decimal system. Compared to binary is 2. The usual one that humans use is 10. We all agree 0 through 9. There's 10 characters that we're looking at. The computer only speaks in binary, which is zeros and ones. So to be able to understand, here is the MAC address of E0. E0 is equivalent to having the first 4 sets being 1, 1, 1, 0. It's also equivalent to 14. It does equal 14. And then the last set, or from that byte, right? Because that's a nibble. So the whole byte, the rest of it would be all zeros. The more we practice the game, trust me, the faster your brain's gonna get to it. I strongly recommend playing this game. I'm gonna be putting you guys into this breakout rooms real soon. But let me first. So the exercise of Flippy Bit, basically, ultimate goal is to understand that there is 2 nibbles within a MAC address. It is represented in hexadecimal, but as we have spoken before, the computer only speaks in binary. So the hexadecimal, which is the human language that we're used to of 0 through 15, does not exist in a hexadecimal. Although the characters are being reused, we all agree that 0 through 9 are in a regular decimal and they still represent themselves here. At the point that we get to 2 digits, it is represented by alpha when we get to 10, Bravo for 11, Charlie for 12, Delta for 13, Echo for 14, and Foxtrot for 15. So each one is a nibble. So 2 characters creates a whole byte of information. There is also a pattern to this mayhem. It always starts off with, obviously, the one all the way to the right, which is your 1. The next guy here is your 2 space, right? The next guy next to him was 4, and the last one is 8. The pattern is as turning on this guy, turning him back off, then to turn on the guy right next to him. Then I turn him back on. It creates a 3. When I turn these 2 guys off, I'm gonna skip them and turn on this guy, which creates my 4, because that is the place of 4 in binary. To get the next number, I repeat my pattern. So now that I have 4, I need to turn on what they consider the 1's place to get the 5. I repeat my pattern again. I turn off my 1 here, and I only turn it on this space, which creates my 6. The pattern continues as always, turning off and on until I completely fill up the whole alphabet, up to F. Any questions on how to read the hexadecimal MAC address and its binary representation?
Probably still need practice.
Yes. And I definitely strongly recommend for you guys to get it all the way up to 256. Actually, no, is it 120, 128 really? 128 is, but 256 is preferred. So it was 0, 1, 2, 4, 8, 16, 32, 64. You get my point. 128, 256, 512, 1024. The further you can go on that binary language, the easier it's going to be for you, especially in circuit sizes and or when we're talking about IPs and subnets. Any questions on how to read this? Doubts? All right, continue on to the next slide. Devices on a visual network. Guys, please mute. Remember to mute yourselves if you're not speaking. Thank you. As we stated before, that the actual devices on the network vary from repeater, a router, a bridge, and a switch. A bridge does exactly that. It bridges one network to the other in a given a confinement, usually in the LAN. Be that it's bridging maybe two LANs or maybe bridging wirelessly. As we said, access points can also be a repeater or a bridge, depending on how it is. Usually bridges two LANs together. A switch is what it is, as we stated before, is where all the actual devices will connect into the LAN to be able to use the resources within the LAN, including a router if the router is connected within the LAN. Any questions?
I have a question. So for the LAN, does it necessarily have to have a router or not necessarily?
Only if you want to get out of the building.
Okay.
A LAN is only as if they need to get out to some type of WAN, be private or public WAN, or a MAN, then you obviously need some type of connection. Otherwise, there's no necessity.
I got a quick question.
Mm-hmm.
Is that repeater a hub or is it just literally a repeater?
A repeater is basically a device that repeats the network. In other words, it's similar to a bridge, but it actually repeats the same network. You can look at it as a lot of times as those Wi-Fi extenders. Those will be repeaters. A bridge bridges two networks together. So the two separate LANs.
Okay, so the bridge is connecting to two mediums, and then the repeater is extending the length of the cable, right?
The repeater can, or the signal, depending if it's wireless, right?
Okay, yeah, because I'm looking at a repeater, and I'm thinking, is that a hub, or maybe it's extending because it reaches 100 meters?
It's very, very similar to, you could think about it, it's almost as similar to a hub, but it's dangerous to say that it's a hub because it's not.
Okay, it's not a hub.
Because a hub could be connected directly to the router and have, so then at that point, it's not repeating the signal or repeating the network. It's meant because of the degradation of signals, per se, of the 300 feet that you have, or 100 meters of limitation, which I think is about 325 feet. I wouldn't go too close to that because Ethernet pretty much degrades when you get very close to that. So the repeater would obviously help you out in that situation and being able to repeat the network to an extended area. It doesn't connect directly to the router. It still goes back to another switch. Any questions? So let's say this computer here wanted to talk to this guy here. He would actually have to traverse the repeater itself, go into the switch, then traverse the bridge, be wherever the bridge is, connection, to get into this network over here. and be able to connect to this computer. And even if he wanted to go out the router, he would have to obviously go that route.
I'm actually confused because the switch in the segments, there's like three PCs sharing the same segment. Does the bridge divide that up?
The bridge is very, very similar looking of a switch. Matter of fact, there's a lot of switches that can be a bridge, could be a switch, or they could be a repeater. It's depending on the job that you want. So if you look at it, all it's doing is allowing this LAN where these switches are, bridge to this LAN that's out here. It's LAN. It's not like a WAN where traditionally you could think of it that it may be a router might be in the middle here. Here's a better picture of the representation. There's a hub, a bridge in the middle connecting these two LANs. They're usually completely different subnets. They're not in the same subnet. If they were in the same exact subnet, then that would be, excuse me, that would be a repeater. It can be the exact same device, just the job that it's doing. If you'll see here, here's a picture of the actual device itself. And it has the ports available to bridge the two networks. Very close to doing the job of a router, but it doesn't give you WAN access. There's no WAN access. The bridge is also on layer 2. He speaks in layer 2.
Okay, so on the diagram, are they sharing the same cable or is it a different cable?
The diagram is just a representation of how they're linked. There is no same cable. No.
Okay. I thought they were using the same cable.
No, that's just their representation of how things connect to each other. But if you see here, there's 2 ports.
Okay, I got it. Thank you.
Okay, I have one last question.
Yeah.
And I keep going back to LAN, but the only thing that's like not clear, I guess, it's the fact that like wireless LAN and LAN are essentially the same thing. However, wireless LAN is connected wirelessly and LAN is connected through like what,
LAN is a physical cable. It requires an actual switch or a hub or something that basically gives you a physical hard connection.
Okay, so then the local network, the LAN will be connected essentially to that by a hard wire.
Yes. So here we are. So.
Okay. Alrighty. Sounds good. Thank you. But that hard wire is not it's not a router, right?
Which one? I'm sorry. Repeat the question.
The cable that connects essentially the local area network, the LAN, is not a router itself, is it?
No. Usually in big, humongous facilities, unless if they have an all-in-one device like you do in your house, they have something like this. These are the server rooms. So all these cables run into this server room here. And they all go to the panels that are on your walls. So the panels that are in your ports that you see, like your telephone cable port on the wall, they all go into that main distribution frame that I keep on mentioning, MDF, main distribution frame. Now this thing wants to go into something that I don't want to go into. So all of these link here and they connect directly to a switch. The switch is the one that connects all devices on a LAN, including a router. A router can connect to the switch and say, hey, by the way, if you cannot if you cannot communicate with somebody, you can't find anybody, I'm here. I can take care of it. I'll look for them out there. That's what happens basically. So the router is waiting. And the moment that I, the switch, say, hey, Carlos, are you here?
So essentially that's what would make it a wireless LAN essentially.
A wireless LAN is exactly like a LAN. The only variance is instead of using physical cables, is using the wireless communication to mimic the local area network.
Right, but what were you saying? Like when you connect, let's say, a router to a switch.
Okay, so yeah, that was me. My pause was actually me waiting for no computer to respond. The moment that the computer does not respond, and when I yell out, Carlos, are you here? The router will take that and say, give me a second. Then he just basically sends it out. The computer name.
So essentially what I'm saying is like once you connect a router to the switch, it automatically becomes a wireless LAN.
No, no, the router only gives me WAN, wide area network.
Oh yeah, okay.
An access point gives me wireless LAN. A router's job is to route you to the WAN, wide area network. He works on IPs and some other protocols.
What would be the access point for the wireless LAN then? Exactly.
The access point is the device for the LAN, and the wireless communication would be the media. Instead of a cable, the wireless communication, it's its media. That's how it traverses.
But what device is that access point if it's not a router? I guess that's my question.
The access point can do 3 jobs. It can do a hub, it can do a bridge, it can be a switch, and some of them also have the capability of being a router. But the access point pelao, the main thing it is that it's a wireless switch or a repeater or a bridge. One of those 3 jobs it takes on. It's either a bridge, a repeater.
Okay, like now it makes complete sense. Perfect. Thank you so much.
Just like there's some sophisticated switches that can do the bridge, a switch job, and a repeater job. That's what the access points job is exactly like that. And you can actually put them at ad hoc and put them as stupid as being a hub version kind of thing. But obviously we don't want to do something like that. Any other questions on the variance between the device, the media, and or the actual technology variance of LAN, WAN? We all understand? Oh, that was pretty good. I'm now a rapper and I didn't know it. Okay, next slide. Hubs. We alluded to these guys. These guys are very, very dumb. They basically, as I stated, even if Carlos tell me he's here, I still yell it out to everybody, the conversation. So basically, it's like that annoying little guy that you hear sometimes in when they're doing a interview, that the guy is speaking in English, but your mom's watching the television in Spanish, so you hear him in English and the guy is repeating everything in Spanish. That's how annoying it is. He's repeating word for word of everyone's conversation. So what happens? There's collisions. If everyone starts talking, I go crazy because I'm trying to talk to everybody about everything that's going on. So you could just imagine this same guy that's trying to translate from English to Spanish, trying to translate everybody in the crowd conversation. It's ridiculous. And it gets annoying. It's not very effective. Ethernet came up with some type of technology to help with the actual collision issue, but the hubs themselves never really had that problem. We're able to fix that problem. Ethernet does. So if I have a token ring hub or something like that, that doesn't have it. But Ethernet technology does obviously help with that. That's one reason why switches came about, and they're much more sophisticated than the hub.
I got
Any
a question. A hub is a layer 1 then, right? Because it doesn't have any frame capabilities.
I'm sorry?
A hub is a layer 1, right? It's physical.
That is
because
correct.
It can't do frames.
It's as good as a NIC card. It's a layer 1.
Wait, I thought a NIC is a layer 2.
And nowadays, layer 1 and 2, yes. But I'm saying it, the physical NIC card is a layer 1.
Okay, so traditionally a NIC card is the physical.
Between 1 and 2 because of the MAC address. The MAC address itself is the one that, but the physical card is layer 1.
Got it. Oh, okay.
It
Thank you.
gets tricky because when you're going to replace the NIC card, what is it? It's a physical layer. If the MAC address on it now, that is on the layer 2.
Oh, I think I get what you mean. There's the physical part, and then the frame is the information. within the logo.
Exactly. That's in layer 2. But the physical, if I can touch it, that's layer 1. I don't care what it is, even the switch. I touch it. I love you, man. That's that's physical switch. But it speaks in layer 2. Gets very confusing. But we need to know these variances because depending where we are in the computer world, we always start in the least intrusive. In the least intrusive, when it comes to everything except for the network, the least intrusive is always we start from the application layer and then we go and dig all the way up to the layer, which is the physical layer. I'll dig in and touch the computer inside. When it comes to the network, it's actually backwards. You have to know these layers because now I got to start from the physical layer. Is the cable in? Is the switch on? All these things I need to check. Are the lights flickering? Next, I go into the MAC layer. Can I get a MBT stat information or a net stat information from my computer that confirms that I can get to that? Then I can go to the next layer, which is layer 3. That would be the routers, my IPs. It gets difficult because if we don't know which one is speaking and what, we'll start looking in the wrong place.
So are you saying that level 1 is the physical thing? So
Physical layer. We're going to be
layer.
learning that, I believe, in TCP/IP stack, which is in our next one. We'll get into details of that. But the physical layer is anything you can touch. If you physically touch it, it's physical.
Would layer 2 be essentially the backend of the computer?
The MAC addresses. All MAC addresses, I think Apple has a different thing, and some other ones have a different thing. But the MAC addresses and the layer of talking is it also speaks in a certain language at that layer. The topology is different. That's already the MAC address. That's the second layer. It is a layer 2 device. But given that it's a layer 2 device, it has everything below it. It has capabilities of 1 to 2. A router speaks in layer 3, but at the same time, it has a MAC address and it has physical layer. Its main job and everything it does is in IP. Its job and everything is in IP. That's where it does everything. But it does contain a MAC address. It has that. And to be able to talk to the switches, right? And it has a physical nature. I can touch it, the physical cards on it, the T1 card that I may put in there, or any WIC card that I may put in.
Okay, so layer 2 is essentially just the MAC address itself.
In layman's term, that's where you are. There is some more like topologies and things that is talking on protocols there, but we'll get into that in later. But that's already on that level. So we know how smart are these devices, how high in these application layers they can go. A hub we know is as dumb as it gets. He's physically there. Yes, he gives you connections, but he doesn't have anything. He can care less about MAC addresses. He just continuously yells out to everybody the information. As you can see, that obviously is very slow. And as we stated earlier, a lot of these access points, if they're not sophisticated enough, they're usually considered that portion of the wireless connection as hubs, because that's what in essence is doing. It's just hubbing the information. Although it has an internal switch, or the switch portion, the physical switch portion, it just really just relays his message to everybody. You understand what that means? So when the wireless access point is going to send something to your laptop, you best bet that everybody that is in that wireless network is hearing your conversation. There is no filter. If I'm on your SID, on your security identifier, right? If I'm already connected to that wireless and the messages get broadcast, if I have a sniffer, I can see your conversation. The computer itself usually won't listen because you're not, when they broadcast a message, it's sending it with a MAC address. So it's going to say who it belongs to. When my access point my wireless NIC card normally is going to ignore it. But if I want to be intrusive and I want to listen in, I can, because it's broadcasting as a hub. It's broadcasting everything wirelessly. Any questions? Any doubts? Switches. Similar to hubs, except it actually evaluates the information and it sends the packets. As I stated before, it has the MAC addresses, it attaches more nodes, and it has its own broadcasting domain. Every single switch port has its own broadcast domain versus the hub, everybody's in the same broadcast domain. So every port has its own broadcast domain. Reduces obviously the problem with collisions, and obviously it's been widely now been, how you say, sunsetting out all the hubs. Pretty much everybody's gotten rid of hubs. I haven't seen hubs for a long time. All right, guys, we're at the 12 o'clock hour. I know we've been having a little bit too much fun, and I don't think we're really finished yet. I'm not sure what page am I in here? It doesn't tell me. You guys want to continue real quick, or I'm not sure up to where am I?
We still got like 20 more slides.
No, yeah.
Shows you're on page 20.
Yeah, we're on 20. No, that's gonna take us a while. So we'll pause here, guys, if you don't mind.
No.
Go to lunch.
All right. See you at 101.
See ya.
See you in 101.
Lisa, you saw my message?
Message. I'm answering here right now, Christina. So what happened? So did you try to log in?
I want to see like what the subscription like has in it, like what was offered.
Any questions in the variances between a hub or a switch on a LAN? We're going to get into the details of TCP/IP and how these things function. That'll be the next session, but just I want to make sure you guys at least understand the actual jobs that they do, where they lie. So over here, we have bridges. As I stated before, they're connected between two physical dissimilar networks, right? Be usually different, either topology sometimes or even different subnets. A gateway, usually referred to sometimes as a router or a device that gives you a connection towards the actual internet. Connection between two logical dissimilar networks. One's physical, the other one's logical. Question.
Yeah, I have a
Router.
question. Can you explain logically dissimilar?
Can we
What
explain?
exactly that means? Like when you say
You
logically
have LAN
dissimilar,
to WAN. You see how the technology here is LAN to WAN, tokering to Ethernet. That would be a gateway. A bridge will connect fiber optic to Ethernet, wired Ethernet to wireless Ethernet. Physically dissimilar. while this here is more in terms of how the technology is using it, because token ring switches or token ring technology uses different devices. Ethernet uses different devices to connect, and the language is different. The gateway will help you to connect those dissimilar type of networks, the way they communicate, the language that they're speaking in. The bridge is going to get the physical layer. You can think of it, this one maybe as in the MAC or the layer 2 as a logical. And then over here, this is the physical layer. So it gets wired to wireless Ethernet, fiber optic to Ethernet physically, anything that is dissimilar within those. That's the variance between the two. That help out a little?
So gateway is networks, bridge is not the media, but, or would it be the media? Like Ethernet, LAN, WAN, those are different networks.
Correct. Token ring is a type of network, and so is Ethernet.
And then fiber optic and Ethernet are just two
cables, right? The fiber optic cable to Ethernet. So that was the device that we saw with 2 ports. So you will connect those 2 ports to that device.
Okay.
And it will bridge the connection between the two.
Okay.
Almost similar to what an adapter does, but obviously much more sophisticated. I don't want to go into that lower layer because that's not what it's doing. But you can think about it as that aspect. But this is a network aspect here. Fiber optics speak in light. Their language is completely different than the copper signaling that's going on. We agree. Same thing with the wired Ethernet versus the wireless Ethernet. They're using 2 different technologies to be able to communicate with each other. And that's what the device does. Just bridges those 2 dissimilar physical networks together. Any other questions? So LAN to WAN would be obviously the gateway. What it means is instead of speaking in MAC addresses, it'll translate into IPs. For instance. Next one is our routers. Our routers here, this is probably similar to ones that you may have. Maybe they don't have that many antennas. Does anybody know why some of these routers have so many antennas?
The doublets, it's to make sure that it gets the person, basically, redundancy.
Yes. What other good features does that give you besides redundancy? What's the major flaw about an access point?
If one access,
one access
if one access point, which would be one of the doublets, start having interference, you have another one to single it, and you can also do single boosting. And some access points have one for receiving and one for sending.
Okay. Now there is some monsters out there that has about 8 of them, and the major reason is this is, as I stated before, just not the router portion here, just the access point portion. We stated a little minutes ago. It has the functionality just like a hub. So what they've come out is actually to create all these antennas and their own separate, per se, broadcast domain. So now that several people can be talking at the same time, versus in this one here, you see 4. I've seen 6 and I think up to 8 antennas on some of these puppies, the ones that are access point only. And that's obviously to alleviate the problem and having to retransmit or wait because obviously it's saturated. Here we're looking at different variants type of routers, and the bottom one is what they call the SOHO router, which has an integrated access point, and it usually also has a switch in the back. On top of having the functionality of being a router, some of them have a DSL port, the other ones sometimes have the cable port. Either which way, those ports are the ones that give you access towards the WAN. all routers forward packets based on decisions of routing tables. These tables that they have within is basically what routes they can take out into the internet. Based on the actual IP itself, it can decide if it's going to send it this way or that way, whatever connection. Some of them only have one connection, don't have various connections, and puts all eggs in one basket. So you're pretty much out of luck. But that's a lot of cases. What happens is that the last mile is really your provider. So not until you get into the provider's actual, what you want to call backbone, is when you're in the internet. So you're going to have to understand, yes, you do have connection to the internet, but most cases you're running on their backbone, which is several miles away, and not until you get into their facility do you have then a connection directly into the internet, which most likely has redundancy. But if anything happens in that last mile, which is usually what they reference whenever you hear the word last mile, it's the POP, your actual service provider. So this router is able to take all instructions from the LAN that is being given by the switch and now adds the IP information. And he actually routes information based on you. He does not actually, no one knows if you do it right, who you are, unless if there's a public IP. But usually no one knows your real IP. It's the router that talks on your behalf, and he actually puts a port. In that port, he says who you are, and he holds you there while he sends out into the internet the request. It comes always back to him. He already knows, because as soon as it comes back, it's going to come to a specific port, to the router. That port I already reserved for you, and it comes back down. That is his job, is to be able to route all these packets that are going in and out of the building. It does not route packages on the LAN. It never even talks, well, I mean, never routes packages, not that it doesn't talk. It never has to route anything, because we already said the LAN speaks in layer 2, doesn't even touch this. Firewall. This device is there to protect us. It's a network security device, and it is either software in some cases. A lot of the new OSs have a software firewall host base, and the sophisticated ones are the hardware firewalls. Those are usually in 2 or 3 locations inside some of these businesses. So you'll have here my representation, horrible, of the internet. Then you'll have here your little firewall. Forgive me, it's supposed to be a brick wall. In here, they do what they call a DMZ, demilitarized zone. Then they'll put another firewall to go towards the private network, private WAN. And or LAN, whatever they have. So these puppies make sure that when something's in the internet, it does not get in unless if it's either been already deemed worthy traffic. Some of them do filtering by inspecting it, and based on ACL rules, which is access control list rules, they inspect every single packet coming in and making sure that it's valid. Usually, these stateful ones, though, allow traffic originating from inside the network and blocks traffic originating from the internet. Now, the stateful one is obviously a little different. That one's in reference to it checking if I started or not. The difference is that the packet filtering firewalls obviously inspects all of the actual packets and checks it against the ACL rules. Versus this one, if I initiated the traffic and it was valid, he automatically kind of put an entry and saying, okay, DeAndre's talking to Phil out in the internet. And when Phil comes back and says, here, this is the information DeAndre wanted, I already have a table saying, well, yeah, he was talking to Phil. This can go through. But now Bob wants to talk to DeAndre. And I look at him, I'm like, well, no, DeAndre never even talked to you. So you're not coming in. That's the difference there. On the ACL, an access control list has a full list. This list can be either a white list or a black list. The whitelist is basically saying what you're going to allow. So you're going to have a whole string of commands coming down of allows. All firewalls always have at the end an invisible line that says deny all. So if I don't put anything inside a firewall, it will deny all traffic in and out. That's why you need to be able to obviously program them and create either a whitelist or a blacklist. Now my whitelist, it will go straight down the line of everything that I have chosen to allow based on any of those rules. As long as it comes to there and it fits that rule, it stops. It's a decision. It doesn't need to continue. So if I'm on step 5 and it says you can do it, I don't need to go anywhere. Boom, go. Now, if I go through a whole list of 500 and I get to the end and you don't have anything there, then I'm sorry, you're not getting in. My list has been completely used. There's no other rule except for the one that I just got to. And it says, I don't trust you. You're not on this list. I'm the bouncer. Can't get in. You're not on a list. Obviously, there's a lot of them that have the mix of the two. The stateful one is pretty decent one because obviously it allows the traffic back in without having to be two-way. You don't have to state it both ways.
I have a question.
Mm-hmm.
ACL. Is there another term for it? Like, for example, stateless firewall, or those are two different things?
There's a stateless firewall. Yeah, there's a stateless firewall. There's stateless ones.
Are they the both same thing, or they're separate?
Let me think about it. Well, this has an access. A stateless one does not have, I believe, really anything except for, we'll look at it. I think it comes up here soon. I believe stateless is different. This is packet filtering. I always get confused because they confuse me with the name. Stateful one allows obviously an originating side of traffic and blocks any traffic on the originating. Then there's a stateless one, which means that the rule only has to be written once. I don't have to write it both ways. On the stateful one, I have to be able to state it both ways. I need to know what's coming in and what's coming out.